Welcome to Secure Software Development. We're going to begin the way we begin every class by talking about secure communication. A common need that we see everywhere is the need for secure communications over an insecure channel. Basically, I need to talk to you and you need to talk to me, but we have to do this over a channel where other people can listen in and eavesdrop. And it's kind of always been that way, right? I send a message, let's say by horseback. I give it to a rider. He rides off into the woods to deliver the message. He can be waylaid and someone can take that message and they can open it up and see what's in it. That's a problem. During World War II, people transmitted messages sort of over the air, right, using RF communications, radio communications. Those radio communications could be intercepted. What do you do about the need to have secure communications over an insecure channel? Well, the classical model is that you use encryption, so that even though they can hear what you're saying, they have no idea what you're talking about. So, for example, you want to log into your bank. You may be sending your username and password. You probably won't exactly be sending your password, but we won't get into that. But you want to send credentials of some form over the internet. And you're going to be sending these over routers and switches and other stuff that neither you nor your bank own or control. Right? Untrusted devices. Okay? And so you can, and you should, assume every packet you send over the internet can be intercepted and read by your worst enemy or by someone who wants to steal your stuff, etc. So encryption is the way to do this, as I said a moment ago. Encryption is the most obvious way to allow this. But for this to work, you and your bank have to agree on an encryption key. Encryption, for practical purposes, is most often symmetric. That is, you use the same key to encrypt and to decrypt. And symmetric keys, we have to agree on that key. So you and I have to agree on what the symmetric key is going to be, and we have to do that over the open internet. So that's a bit of an issue, right? It's a bit of a problem. But it turns out there are methods for doing this. There are various secret sharing methods, and so we can do that. We use some secret sharing method. Maybe we use something like public key cryptography in order to do that. You might think, well, I use public key cryptography to do everything, but you typically don't. You use public key cryptography to exchange credentials that you then use for everything else. Like with SSH, right? With SSH, you have a key pair, and that's used to establish communications. But once you're talking, the overhead of public key cryptography is too high. You want something fast like AES, and that's typically what you're going to use once the connection is established. And that's a symmetric encryption system. So we need to authenticate to the bank. Many ways to do this. The most common way to do it is not to have me send the bank my username and password, but to do something so that the bank can prove to me that it's the bank, and I can prove to the bank that I know the correct password. I just have to prove this. And once I've done that, okay, everything is fine. That way the password doesn't actually have to be transmitted. So, for example, we might generate a large-ish, let's say 16 bytes. Is that big? Well, yeah. I mean, 256-bit encryption is pretty significant, and that is merely 8 bytes. So 16 bytes is getting up there, right? That's beginning to be fairly significant. So we create a challenge, and the bank creates a challenge and sends it to me, and I create a challenge and send it to the bank. So there are two distinct challenges passing in the ether. Now, each one of us is going to use the stored credentials that we have to perform some cryptographic operation on the challenge, and then I will send that result to the other party. So the bank will take my credentials and do an operation. I'll take my credentials and do an operation, and then we send the result back. And now we can check that. So a simple replay won't work because the challenge can be unique almost every time. So the bank can then look at what it got back and say, did you really know what the credentials were? Oh, yes, you did the right thing with this. So you did. I'll consider you authenticated. Or, no, I don't know what you did here, but it didn't seem right. I'm going to reject your authentication. I hope this makes sense so far. Okay, so I send a challenge to the bank. The bank takes my credentials and it does some manipulation to it and sends it back to me. I can then look and say, did it do what should have been done, right? I can take the same challenge, apply my own credentials to it, and see if I get the same thing the bank does. And I send a distinct one to the bank, and it plays the same game. Now, it's possible that I think I'm talking to the bank, but really I'm talking to someone else pretending to be the bank. That's a problem. I can get around that, this person in the middle kind of attack, by potentially using an additional layer of host verification. And for example, SSH does this with host keys. Your browser does this. It tries to verify the identity of the endpoint through a certificate chain. Okay, this is a pretty common technique. We're going to verify the endpoints. Once we agree we know who the endpoints are, then we can do an authentication round. So here is a example of this. This is the Netlogon remote protocol used by Windows to authenticate to a domain controller. Okay. The shared secret is the client's hashed account password. Now that's known, that the hashed password is known to both the client and the server. Both of them know the hashed password. This is not the actual password, but they know the hash for it. Okay. Again, hashes tend to the goal is to have a one-way function for a hash. None of the functions we compute are perfectly one-way functions, but we like to get as computationally close to that as we can. So here we go. The client and the server exchange 8-byte or 64-bit challenges, and you can see that over here on the right. The client sends its challenge to the server sends its challenge to the client, and these are different challenges, presumably. Sure. And so then the client and the server each use both of the challenges and the shared secret, right, the hashed password, to compute a session key. Now, if both of them know the password hash, and since both of them know both of the challenges, they know everything that goes into it. They know the hashed password, they know the challenge that was sent by the client, the challenge that was sent by the server, and so with those three things, they will both compute exactly the same session key, presuming they both know the shared secret. The session key can then be used to communicate both that we know what the shared secret is and should be considered authenticated, and also we can use that to encrypt the traffic, right? Because now we've agreed on a symmetric key, and we can use that to encrypt the traffic. An eavesdropper won't know the shared secret, and so the eavesdropper can't decrypt, we hope, the information being transmitted. There you go. Pretty straightforward, nice and simple. So here's how a piece of that works. So in order to compute the response, each side is going to use AES, the Advanced Encryption Standard. And they're going to combine that with a few pieces. So we take the thing that we're going to apply AES to, we would call the plain text, and we're going to then encrypt it byte by byte. Now, we need a full chunk of bytes in order to do this, so we tack on the front of it an initialization vector. And you can see that over here in yellow and then highlighted in red. This is the initialization vector. And in this case, it's just some random bytes. And that's a pretty good choice, right? You like to have some randomness in there. So we prepend this random bytes before it, and then we put this through AES, and we'll get out a new chunk of bytes. But what we're going to do is we're going to throw away all those bytes except for the first one. Okay? This is all part of the AES CFB8 operation on Windows. So we'll take this first byte, and we will bring it over, and we will exclusive OR the first byte of the plain text message with the result. So that first byte of the plain text message was 01. That's in hexadecimal, and that just means that the 0th bit is set. So the value is just 1. The thing that we're ORing it with is E2, or exclusive ORing it with is E2. And you'll notice for E2, it's even, which means the lowest bit is not set. So when I exclusive OR those, I get ones wherever there's a 1 and a 0, and I get zeros everywhere else. So I'm going to wind up with E2, but with the lowest bit set, or E3. And that goes in. Now, I move this little sliding window I've got along 1 byte, and I consider the next sequence of bytes. I apply AES to it, and I get an output over here. In this case, I get 9A. I then exclusive OR that with O2. Right, that's the next byte of the plain text message. This tells me that the next to lowest bit is set. Right, bit 1 is clear, but bit 0 is clear, but bit 1 is set. Over here I have 9A, and that's hexadecimal. So I care about the low nibble, which is A. A is 8 plus 2, right? 10 is A, and 10 is 8 plus 2. So I know that the second lowest bit is also set here. So the result's going to be that that bit gets cleared. That's how exclusive OR works. And so I'll wind up with 98, and that's what I put in over here. And I just keep marching across in this way. When I'm finished, I don't care about the initial part of it, the part that held the initialization vector. So I throw that away, and now I have this message, which is encrypted, that I can then send. And this message can be of any length. Right? The initialization vector, there's 16 bytes here, that I used in order to get this, but now I can throw it away. What if the two sides don't agree on the initialization vector? Well, that can be a problem. So we will use a standard initialization vector, and Microsoft does. They use all zeros for their initialization vector. And that might initially seem like a terrible choice, and maybe it will still seem like a bad choice when this lecture's over, but keep in mind, we're going to take those bytes and we're going to encrypt them using some AES key, yielding some weird result that we're going to exclusive OR, and we're going to march across, and so we're going to get weird stuff out, right? We're going to do some encryption here. So we're going to take an all zero initialization vector. Now, so we get some key. We don't know what the key is. Okay, we get some key that we derive from this process. Some encryption key for use with AES. That encryption key, when we apply it to all these zeros, we get some sequence of bytes. And this first byte could be anything. There are 256 different possibilities for that first byte. So we have a 1 in 256 chance that we will get something out of that first byte that winds up being, say, 0. Now, why am I interested in that first byte being 0? Well, if that first byte turns out it happens to be 0 after I do the encryption, that's great. That means I exclusive OR 0 with the byte up here. In this, 0 with the byte up here. And in this case, it's 0. But whatever it was, I would just get that byte down here, right? I would copy the clear text straight down without changing it. That's probably a bad thing. So what I would like is a key that gives me a 0 at the start. But I don't get to pick the key. The key is effectively random. So what if I do the following? What if I just try until I get a key that gives me a 0? Because if I keep doing that, I have a 1 in 256 chance each time. So I'll just do it until I get one of those, and I should be able to do that, and it shouldn't take all that long to do it. So I get a 1 in 256 chance that the output will then contain all zeros as well under this approach. Now, you may say, the server is going to lock us out. If I can't just keep asking for new encryption keys. Well, that would be true for a user, but keep in mind, I'm trying to join a domain. I'm a computer, and I get to try as much as I want. So I send my challenge of all zeros. The server sends its challenge. Okay? So we then go through this process, resulting in, an authentication, but only when I can get all zeros. When I get the zeros. At that point, I've gotten an authentication. So, at that point, I'm authenticated to the domain controller, but I don't necessarily still know what the key is. How would I know, right? I don't know. The server sent some random challenge. I sent zeros, but the server sent this random challenge, and I monkeyed with the generated key until such time as I could get all zeros, because then I knew the server and I would agree. And at that point, I'd be authenticated. However, I still wouldn't know the session key. This is a little tricky, so let's go through this again. I send the server all zeros, so I know my part of the challenge. The server sends me theirs. I then, if I don't like that, because I can't get all zeros, I start the whole process over, and I just repeat until I get a server challenge that gives me, with the encryption process, all zeros. At that point, I know that I can authenticate, and I'm done. But I still don't know the session key. Sorry. But that's okay, right? And now, keep in mind, I can't know the session key. Why can't I know the session key? I know both the challenges. I can't know the session key because I don't know the hashed password. All right. Hope all this makes sense. There's a lot going on here, I know, but stay with me. So, I don't know the session key. I never knew the credentials, but that's okay. Because it turns out, now that I am authenticated, I can tell the server, hey, turn off signing and sealing, which means don't encrypt traffic with the session key. And the server says, okay. Once that's done, now I can engage in other activities. For example, maybe I can go ahead and set the server password. That's great. So I'll do something like set the domain controller password at that point. This is bad. What I've done is I've just logged onto the domain and potentially made changes to it as whatever user I want to be without knowing the credentials. So that breaks the whole model. So this is CVE 2020. Came out during our glorious COVID year, 1472. What happened here? Well, there was an assumption about the security of the crypto system. And part of that assumption that was built on the crypto system is that the initialization vector would be something akin to random. And possibly as well that the protocol would use more than maybe just a single byte. It wasn't random. It was all zeros. And in addition, the configuration allows us to turn off encryption. It's not great. This one finally gets an Olympic level score. This gets a perfect 10 with the CVSS. So this is as bad as it gets. And it points out a few things we've been talking about. Weaknesses occur when an assumption is not enforced. And if you're using a secure component, you have to make sure to honor the security assumptions for that particular component. This was probably done for backward compatibility. And then that's important, right? So I come along and I'm going to add encryption to my system. But I have lots of components in my data center, in my enterprise, that don't understand that encryption standard yet because they haven't been upgraded or they're older and they can't be upgraded. And that's all going to break. So maybe I want to be able to turn off encryption for some of those. So I'm valuing backward compatibility. That's important. My organization has a mission to accomplish, and I need stuff to work. But I have to recognize that what I'm doing is I'm valuing that over enhancing security. And that should always be a short-term type of assessment, right? I can't just say, well, this is fine, I'm just going to go forward like this forever. That's not good, right? Presumably, the security is being added for a reason. And maybe I have a short-term need to disable it, but ultimately I have to get to a state where I can be secure again. Also, of course, be aware of the assumptions of the tools you use, especially when you're using something like cryptographic primitives and other kinds of security tools. Security versus backward compatibility is a business decision. That's what it is, right? Suppose you're trying to provide wastewater treatment for a town. Clearly, you don't want to get hacked. But also, you can't just break systems by adding these new features. It takes time to roll this stuff out, and you have to figure out how you're going to deal with it while you roll these new features out. Because you also can't stop wastewater treatment. People depend on that. So it's a business decision. And you have to ask yourself some questions, right? Is this feature important? How important is it? Certainly I want to value it over simple convenience, right? Go do the work to upgrade things. There's going to be some pain associated with that. If the feature is not important, okay, maybe don't include it. But a lot of times the security features are added to address some specific thing that has happened. Security tends to be very reactive. And that's a clue to you that you should try your best to adopt that security profile as fast as you can. All right. Let's go back to threat analysis, and we're going to talk about a slightly more systematic way of doing a threat analysis. We talked about ad hoc threat analysis, and we would like to have something that's maybe a little more systematic, where I can do that work and say, hey, I did a good job, and I can also know that I really did do a good job. Again, threat modeling is a creative exercise. Some days you're going to be more creative than others. Some people are going to be more creative than others. Some people are going to be more creative about certain types of systems on certain days when they've slept well and had a good breakfast. It's all right. There's never going to be a perfect threat model created, but it's helpful to have some guidance in building one. One thing you can do is you can go and use the CWE list. That's a common weakness enumeration. You can just use that. However, if you want to go through all of them for your code, or for your system, keep in mind there are 939 of them, and that's a lot. So maybe instead of using them all, we just use the top 25 of the CWEs, and you see them over there on the right-hand side of the screen. And this is the CWE top 25, considered the top 25 most dangerous weaknesses, ones with the highest score. Now, the advantage to this approach is this is what's happening, right? This uses a lot of evidence. A lot of evidence. A disadvantage is some things might not apply to your particular domain or application, etc. Right? For example, number 2 is improper neutralization of input during web page generation. What if you're not running a web server? Right? Some of these just aren't necessarily going to apply. And so, that's a disadvantage. So maybe the top 25, you need to go a little further. Something that is maybe more targeted is to go and find a list of common threats for your particular domain. So over on the right, we see the OWASP top 10. Right? These are things for the web environment. And, you see the usual stuff there, right? You see injection, insecure design, server-side request, forgery, etc. This has a big advantage in that it's customized to your particular domain, and it focuses on active, persistent, serious threats. And over on the right, you see the 2021 version. That's because they only do it every 4 years, and the 2025 version is being worked on now, and it'll be out in 2025. A disadvantage to this is that this ignores threats that have fallen off the list, right? There are threats just below that last one there that are probably still very relevant and important that you should think about. And it also ignores threats that are just emerging. So maybe what we can do is, when we want to do those, we should do those things as well, right? We should think about those top threats, certainly. But maybe we can think about some broad categories of threats, and we can try to organize our efforts around recognizing which categories apply to which components, and then thinking about, well, it's this category of threats that apply to this particular piece, and let's think about that and try to list the threats associated with that. And if we do that, we might wind up with something like Microsoft's approach, which is STRIDE. STRIDE is an acronym for spoofing, tampering, repudiation, information disclosure, denial of service, and escalation of privileges. And you may think, Microsoft, well, yeah, they actually have invested a lot in security. And this turns out to be a pretty good, it's not huge and complicated, right? You can keep the acronym in your head, right? You've already learned the acronym STRIDE, and with a little bit of work, you'll know what all the letters stand for, and you'll be able to just run down that list whenever you think about something in your system. And that's basically the idea, right? The basic idea is, I've got a database. What if someone spoofed credentials to that database? What if they tampered with that database? What if they were able to modify the logs of the database to hide what they did, or make a change to it, but then go back and erase knowledge of that change? What if they take the information in the database and they give it to WikiLeaks? What if they, hammer my database with a bunch of requests so that no one can use it? Or what if they become the super user and just erase my database? Okay, so you work down that list and you think about the things that can happen from these broad categories of types of attacks. So spoofing is just spoofing your identity, and that violates the authentication property, right? If you look over that middle column there, we see authentication, integrity, non-repudiation, confidentiality, availability, and authorization. So we see the CIA triad: confidentiality, availability, and authentication. And we also see a couple others. We see non-repudiation, and we see authorization, right? These are our two additional ones. And so we're in that other model. We're in the AAA model here. But that's fine. Spoofing identity is pretending to be someone or something other than yourself. And we'll talk a little bit more about these in a moment. Tampering with data, just what it says. Repudiation is claiming that you didn't do something or you were not responsible. Information disclosure, obviously giving out information when you shouldn't. Denial of service, exhausting resources for something. Elevation of privilege is allowing someone to do something they should not be authorized to do. An advantage to Stride is these general cases provide greater coverage, and that can include emerging threats, right? And it encourages you to begin to think maliciously, to think more like an attacker, right? How can I violate the integrity of this system? How can I violate the confidentiality of this system? Get you thinking that way. A disadvantage is that it's very high level. An advantage of the previous ones we saw was they were pretty specific, right? If someone trying to do cross-site scripting, that's a very specific kind of threat, right? These are very general, but that's okay, right? We're still a little bit ad hoc, but now we have some categories to help us organize our thoughts. So let's think about what all these different things are. Spoofing is pretending to be something that you're not. And if you look over on the right-hand side, you can see an example of spoofing the Windows login screen. And there's some code you can download that will let you do that. The link is there and in the notes. So you might pretend to be the login prompt. That's something you pretend to be. You might pretend to be the Windows authentication service. You might pretend to be PK exec. Right? Make your own fake version of PK exec, put it in the user's area. You could pretend to be whatever. You could create a Trojan executable in the user's path. Make your own sudo. So when the user types sudo to do something, you grab those credentials and you're in the middle. You then transfer those and let them elevate. But by then you already captured their credentials. You might spoof your MAC address. It's pretty easy to do. You might spoof your IP address. Don't know, maybe a little more challenging, but can be done depending upon where you're sitting on the internet. You can pretend to be a user you're not, right? At the end of the day, just pretend you belong. And if you're assertive enough about that, you may get away with it. Another thing we might do is tamper with a field. For example, there may be hidden fields within a web page. Over on the left, you can see that exactly. That's what's going on. Developer mode has been opened up. You're looking at the source to it. Find an entry that says is admin. We'll just paste true in there. Suddenly, that's what's in the web page. We save. That information goes back. And if you look up at the top, you'll see that suddenly now we have an admin menu because now the system thinks that we're an admin. Lots of things you can do here. You can intercept and change data on the network, overwrite temp files, change permissions, modify a user's path, change web parameters, change URLs. right? Or do what we're seeing over here, find hidden fields in a web page and change them. Lots of information is leaked out through fields in the source of web pages. Repudiate, right? Deny everything, okay? Deny everything. Insist you did not receive a shipment. You didn't click the button. You didn't use someone else's login. Make them prove that somehow you did. Well, the way they might try to do it is by using things like logs, which is where tools like you see over on the left-hand side, or sorry, the right-hand side, come in. There are tools to let you modify and clear the logs. Windows is a little bit more rigorous in some ways than Linux in this regard, but you can still get there. So if there are logs, you should consider tampering with them, spoofing entries, etc. Another thing, disclose information. Right? Learn the hidden stuff. Go and look in temporary files. Temp files are often not encrypted. They're often world readable. They're sitting in the temp folder. Just go and poke around and see what's there. Go and see what's in the process list. Weirdly enough, sometimes processes start other processes with command line arguments that occasionally include things like usernames and passwords in the clear because they're just starting at the command line. Those end up in the process listing and you can see them. What's in readable files? What's in the file name? Sometimes the file names will give information away. Cause error messages and then look carefully at what's in that error message, or trigger a logging message and look at carefully at what's in that logging message. Okay, check all the logs. Over on the left-hand side, you see an example of that. This is a pretty critical one, 9.8. In this case, a piece of software allowed attackers to gain administrator access because verbose logging wrote the administrator password into a world-readable file. Not the best for security. Go and look at that stuff. People reveal stuff like that all the time. Go find side channels. Okay? Go look at the web parameters. Go read the cookies that you're being asked to store in your browser. Talk to other users who use the system. Complain to IT about access problems. Like, this doesn't work for me. Why isn't this working? Why I can't get into this particular database? I've got I just can't get in. See what they tell you. They may tell you important information that you can use. Denial of service, right? Use up all the things. Fill up the temp file system. Things are going to break when you do that. Fill the process table. Stuff's probably going to break when you do that. Bind up all the sockets. Allocate all the disk space. Take any finite resource and just use it all. Or use a lot of most of a lot of different things. Deadlock the system. Get it into a live lock. Disconnect stuff. Disable stuff, etc. Over on the right, we see a odd little sequence of characters. That is a bash fork bomb. It declares a function named colon, then it calls colon, pipes the output of it to colon, puts that in the background, and then thus repeatedly running itself recursively, and at the end, after the semicolon, it calls the function colon. It's a cutesy little thing. It's pretty effective. Elevate privilege, right? The idea here is just be all you can be. Can you become root? Can you become administrator? Could you get a job in management? Maybe that's the easiest way to elevate your privilege. Or get a job in IT. They'll give you some of the passwords. There you go. Once you're in a company, request additional privileges. Say, I'd like to have that. They'll often tell you how to get it, and you can maybe go do some training, and now you have that privilege. Join all the groups. Just join all the groups because that gives you the widest view. Steal passwords, crack passwords, steal cryptographic keys. Poke around on the system. People will leave their SSH creds out in little folders. Sometimes people copy them to a central repo because they want to use the same SSH cred across a bunch of different machines. Go and find recovery keys. People leave those things lying around. Go and sign up for a training in your class. It looks good on your resume. It looks good to your boss, and it may give you more access. Create a spoofed application and then complain about it to IT, right? Spoof something and then say, this isn't working. Here, take a look at this. I can't log in. And let them enter their credentials into the application. All of this stuff is stuff you can do. Go over on the left-hand side. It's a video, in this case, that you can click through and watch. It's a local privilege escalation on Ubuntu. So it's a way to trick Ubuntu, and in particular, trick the desktop manager into thinking, oh, I need to create a new user. Here you go. And you can build a user with administrative privileges, and then suddenly you're in the sudo group and you're good to go. A lot of stuff going on here. For spoofing, does any part of your system rely on authentication of users, of software, of servers, or of data, right? Do you need to check the authenticity of your data? You should consider doing that. Consider the impact of spoofing that. What if someone gives you bad data? Would you know? What if you're connecting to a server, but it's not the server you think? Tampering. Is any part of your system modifiable by the user? What happens if the user modifies that outside the normal scope of operations? Right? So you've got a configuration file. Can the user just go and tinker with that? And if they do, is that okay? And if it's not okay, could you detect it? Repudiation. Do you keep logs? Right? Are your logs secure? No. Anyone can write to the logs. Well, then you're not keeping logs. And what are the things that you do but you don't bother to log them? Should you log them? Maybe. Information disclosure. What information must you keep secret? Right? Because there's a law, because it's good practice, because you're concerned about it getting out. What do you need to keep secret? And how do you store it? Do you have security when the data is at rest? Right? It's encrypted on the drive or not. How do you move it? That's security in motion. Is it encrypted? What do you do? Minimize the information you give out to unknown users. Right? Don't write out passwords in log files. Don't write out sensitive information in error messages. Minimize the information you give out to the bare minimum that you need to communicate to the user what's happening. Beyond that, be very careful, because you can end up giving away inadvertently information that helps an attacker. What if your software runs out of some resource, runs out of memory? How do you handle that? Does your code actually handle running out of memory, or does it just fail? Is it okay for it to fail? Sometimes it is. That's fine. Sometimes it's not, and you need to do something else. Running out of disk, running out of time. Right? Does your software gracefully degrade? Okay? I mean, just falling over, that could be an option for some things, but for certain critical operations, it might not be. And does your application have privileges or rely on privileges? And how does it manage those? Right? Does it protect against attacks of someone trying to steal or elevate privilege? Because if your application, for example, has the ability to do privilege elevation, someone might use your application to do privilege elevation. So I'm pointing you to the Microsoft Threat Modeling tool. Now, it's only for Windows, so if you're not a Windows user and you've got a Windows VM, sorry. It's actually a really cool tool. It helps you do your drawing. So you do your drawing, you can see up there in the top of the screen. Once you've done that, the Stride tool comes down and it tries to suggest a whole bunch of different things that you might want to consider. And it's kind of neat in that regard. Most of them don't go this extra step and try to suggest all this stuff, because you might have to delete a lot of that and rebuild it. But in this case, it does, and it's pretty helpful. And you can watch the video to see how that works. And if you are a Windows user, it's a free download, and it's a pretty neat little tool. Homework. For homework, I want you to go and work with the threat modeling tool. In this case, we're going to use the OWASP Threat Dragon. You can install it natively on Windows, on Mac, on Linux, in a VM, in a container, a million different ways to do it. I found the Linux version seemed to work better when I used the snap, but your mileage may vary. What I want you to do is create a threat model of an external user interacting with the web server using a backing Git repository. So you got an external user, some client, you got a web server, and then you got a Git repo. Server talks to the Git repo, client talks to the server. Nothing too complicated here. So you should create those three things: an actor, a process, and a store, and then add trust boundaries and information flows. And before you start overthinking it, don't. You should wind up with something that looks just like what I have over here, my this poorly drawn thing here. Okay, the dashed lines are trust boundaries. So I have a trust boundary that exists between the client and the web server, and I have a trust boundary that exists between the web server and the GitHub repo. The client is an actor, the web service is a service, and the repo is a store, right? They all have little different shapes in this modeling language. So client is that dashed rectangle, server is a circle, and the GitHub repo has those top and bottom lines. And you can see I've connected them, right? The client sends requests to the web server, which sends back a response. The web server writes to the GitHub repo, which can then read the information back from it. Okay? As you enter this information, there'll be little checkboxes in there. You should pay attention to those. The user provides authentication. Flows between the client and the web server are encrypted. Okay? So those are things you might want to look for. And checking those boxes or not checking those boxes can change a little bit what the tool offers you in terms of different possibilities for threats. What I mean by that? For each one of the components, you don't necessarily get to enter all of the information. For a process, yes, you can enter anything from the whole stride spectrum. But for an actor, you can only talk about that actor spoofing or repudiating an action. You can't talk about tampering, etc. The tool is set up to try to guide you in the right direction on this. So not every element admits every threat category. So what are you going to do? You're going to go through and you're going to try to identify and include at least one threat for every element. Sit there and think about it. Try to think about what a threat might be for that. And again, the tool is going to provide you with a little pull down, which will have the ones that are relevant. So for example, the pull down for the GitHub repo, which is the store, is going to offer you tampering, repudiation, information disclosure, and denial of service. Pick one of those and give me an example of how that might happen. Once you've done that, and again, I gave you the picture. I'm not trying to make you do a lot of deep thinking or give you a lot of busy work. I just want you to get a general, I want you to do a little bit of thinking about threats and use a threat modeling tool to get a little bit of experience with it. Okay, that's the point of this experience, is to just give you a little bit of experience with threat modeling. Okay. When you're done with all of this, export your model as a PDF and upload it. And you'll find that you can export. There's a menu up at the top. You'll find export PDF on there. Just export it to a PDF and then upload that. That's it.